Okay, we're going to review polar graphs and then look at some calculus with some polar graphs. Very important. I want to review polar graphs because the calculus heavily depends on knowing how the graph looks. So let's make sure we remember. So remember that coordinate system is different than the rectangular coordinate system, where we have a pole, right? And then we have a polar axis. And then we have a point. All right, so this point right here, that would be your point. It's always in the format of r comma theta. So it's always a radius comma theta. Theta is the angle that is created by starting at the polar axis and going toward that vector. R is the length of that vector. All right, so make sure that you're good with that. Because of this, we can represent the same point in many different ways. So that's something else that's going to affect our calculus a little bit. You'll see a little bit later. So for example, if I wanted to talk about this point over here. All right, this point over here, let's say this is a radius of 2, and the theta is pi. That's one way to represent that point in polar. But another way is to think of it as it's a -2 radius, and it's at the point 0, or the theta 0, or it could even be 2 pi. So again, you got to keep in mind that there's many ways to think of that. Ways to convert from polar to rectangular, since we are working with angles and radii, then it lends itself to trig. So remember, if I have this theta and this r, and there's my point, all right, we would normally call that point x and y in rectangular form. So our x would be this side of the right triangle, the y would be that side of the right triangle. So x is r times the cosine of theta. Keep in mind that if I do cosine, that's x over r. So x equals r cosine of theta. Y equals r sine of theta. Hopefully this looks familiar. And then if I wanted to relate just the sides, x squared plus y squared equals r squared. Okay, so reminder about how to convert from there. And then if I want to start with rectangular and go to polar, then we can use the tangent, because x and y is what we'll start with, and that's opposite and adjacent sides. So tangent of theta is equal to y over x. You can also say that r is the square root of x squared plus y squared. Okay, so that's how you can get your theta and your r from x and y. Let's look at a few examples. Okay, so it says convert r equals -4. Notice that this is a polar equation, and it does not have theta in it. So that means theta can be any angle. Any angle. So if I say, okay, any angle as long as the radius is -4. So let's say I start at 0, all right, and then I go -4. That would be over here. Well, what if my angle is at 90 degrees, or pi over 2? That would be down here, and so on. So it would be all of these different points that have a radius of -4. So what does that make? That makes a circle. Notice that it's a lot easier to draw polar equations and polar curves on a polar grid. Now, if I wanted to convert that to rectangular, then I would say, okay, r squared is equal to -4 squared. So r squared is equal to 16. The reason I'm doing r squared is because we said that x squared plus y squared equals r squared. And that would be how we do an equation of a circle and rectangular. Right? And we would have that. Okay, so that's a simple one. Now, if we have an equation that says theta equals pi over 4, notice that this is any radius. So if I just say, okay, it doesn't matter what my radius is, positive, negative, whatever, but it has to be theta is pi over 4, so that's at 45 degrees. All right, so if it's 0 radius or 1 radius or 2 radii, so on, it's this line where I could go negative. So this is just a straight line when I have theta equals pi over 4. Now remember, we said to convert to, we have tangent of theta is, tangent of pi over 4 is equal to y over x. All right, we know the tangent of pi over 4 is just 1. And then if I multiply both sides by x, then I get y equals x, which is what we're more familiar with. It has a y-intercept of 0 and a slope of 1. Okay, so you can see how those relate to each other. So now let's do some harder ones. These have both radius and theta in them. All right, so again, we want to solve this for cosine of theta. That would be equal to r over 6. And remember that cosine of theta is equal to x over r. That's from our conversion. So if I set those equal, I would have x over r is equal to r over 6. Cross multiply, and I have r squared is equal to 6x. And we already know r squared is the same thing as x squared plus y squared. Now what do I do with this? This, we're more familiar if it looks like a conic. So let's move that 6x over and complete the square. So remember, if I move that over, I just have 0. And I added 9 on the left, so I have to add 9 on the right. So this is going to be x minus 3 quantity squared plus y squared equals 9. So this is a circle with a center at 3, 0 and a radius of 3. When we look at the general graphs of these, you'll see this is the y behind why we know that's a circle. Okay, so let's look at the next one, example 4. Let's practice graphing just without converting to rectangular. Let's just graph with our theta and our radius. Okay, so again, you definitely want to try going through 2 pi, but some of these have cycles that are not just 2 pi. So again, you have to be careful as you're graphing this and understand the y behind everything. So if I have 3 theta, think about some thetas that would be good. We'll definitely want to plug in 0. All right, but we want to have denominators that are reducible by like 3. All right, so something like pi over 6. Also, we want to use the ones that are nice on here. So this is pi over 6. This was the pi over 4 that we've already done. This is pi over 3. We can get smaller and do pi's over 12s. But again, that unit circle will help you. We can plug that pi over 4 in just to get a nice point. Let's see, pi over 3 and pi over 2. Let's start there and see what we get. So if we plug in 0, we just get 2. Because cosine of 0 is 1, 2 times 1 is 2. Pi over 6, so that'll be the cosine of pi over 2, which is 0. So 0 times 2 would be 0. Now here's why we might want a pi over 4. If we plug in pi over 4, we get negative square root of 2, which is about negative 1.41. Okay, so it might be nice just to have other points besides just 2's and 0's. All right, pi over 3, that'll be a negative 1, so negative 2. And then pi over 2 will be 0. So let's see what's happening there so far. So 0 is at 2. Pi over 6 is at 0. Pi over 4 is at negative 1.4. So that's, I have to go negative 1 and then a little bit more than that. So like right there. And then pi over 3 is at negative 2, so pi over 3, but we have to go to the negative 2, so that's this in that quadrant. And then at pi over 2, we're at 0 again. So far, it's like we've traced this. Okay, so pi over 2. So that's all we've done so far. So obviously we're not finished. So if we keep going into other quadrants, so like 2 pi over 3 would be 2. 3 pi over 4, that ends up being positive square root of 2, which is like positive 1.41. If I do 5 pi over 6, that'll be 0. And then pi will be negative 2. So let's see what we got after doing that. So we left off at pi over 2. 2 pi over 3 is at 2. So again, here's my 2 pi over 3. And I have a positive radius of 2, so that's right here. And then 3 pi over 4 is a positive 1.4. So that's like about there. 5 pi over 6, reminder where that is. Okay, so then that's at 0 again. And then at pi, we're at negative 2. So if I'm at pi, I come back to negative 2. So when I trace that out, it looks like this. Okay, so it looks like a little leaf. So we ended up where we started. So that means my cycle's complete, and we didn't even have to go through all of the quadrants. So again, that's what I mean by it's important to know how the graph works and the full cycle that it is. Okay, so reminder, that was all reminder about polar. Let's look at slope and polar form. Okay, so we have f as a differentiable function of theta. The slope of the tangent line to the graph of r equals, r is the same thing as f of theta, at the point r theta is. So we're looking at the derivative, right? The slope of the tangent line, dy dx, is going to be dy d theta over dx d theta. So again, it's just like in parametric. So if we do that, keep in mind that y was r sine of theta. So if I do dy d theta, then that's going to be r cosine of theta plus r prime sine of theta. All right, if I do x, again, we're treating this like a parametric, r cosine of theta. So dx d theta is simply negative r sine of theta plus r prime cosine of theta. Pause that if you need to absorb that. So then if I just switch, instead of r's, I'm going to put f primes of theta, or f thetas. So my dy dx we said was r cosine, so that's going to be f theta cosine of theta plus f prime of theta sine of theta. So all I'm doing is replacing the r's. And then I have negative f of theta sine of theta plus f prime of theta cosine of theta. All right, and all this is, of course, is that the dx dy is not equal to 0, or the dx d theta, the bottom. We don't want the denominator to be equal to 0. Sorry, that should say dx d theta, not dx dy, at r comma theta. So let's look at tangents then, okay? Some specific tangents we care about, horizontal and vertical tangents. So horizontal tangents occur when your derivative equals 0. So that would mean when our dy d theta equals 0. And then vertical tangents occur when our derivative is undefined. So that would be when dx d theta equals 0. If dy d theta and dx d theta are simultaneously 0, then no conclusion can be made. Then we really have to look at the graph. No conclusion can be made about the tangent lines anyway. A good example is in your book, so if you need to pause and go get a book, please do that. But it's on page 734. Okay, so if you look at that graph, looks like this. Okay, so they do all the work to show where the vertical tangents are and your horizontal tangents. Okay, and then they show you how the dy d theta and dx d theta are both 0 at this point. So look at what's happening. We can't really figure out what's happening there unless we look at the graph, and that's a cusp point. So really it's just undefined there. Okay, so, and think about that makes sense in what we're doing. If both of these are 0, then we have 0 over 0. That's an indeterminate form, right? So when things are indeterminate, we have to use other tools and resources to figure out what's going on there. All right, so let's do an example. Find the horizontal and vertical tangents of this polar equation. All right, so keep in mind, x is equal to r cosine of theta. Y is equal to r sine of theta. Remember, we're doing our derivatives in parametric form. Okay, so if I do x is equal to 2. So all I'm doing is, instead of having r here, I'm replacing it with what r is equal to. So 2 sine of theta, cosine of theta. And then my y is just 2 sine squared of theta. Okay, so now, if I do the derivative, let's do the dx d theta. Remember, these are going to give us our vertical tangents if we set them equal to 0. So my dx d theta is going to be negative 2 sine squared theta plus 2 cosine squared theta. So I'm just doing product rule. I'm going to simplify this a little bit. So if I factor out the 2 and switch which one's positive, I'm just going to reverse the order. So I'm going to have 2 cosine squared of theta minus sine squared theta. This is a double angle identity. So dx d theta is equal to 2 cosine of 2 theta. So this part is the double angle. All right, and again, if you need to go back and review those, please do that. Now, why would I want to do that? Remember, we're trying to set this equal to 0 and solve. So this is going to be an easier equation to solve as long as there's only one trig function going on in there. So this is going to be where 0 is equal to cosine of 2 theta. Remember, when you have a double angle, 2 theta is equal to pi over 2, 3 pi over 2. Remember, you want to increase your cycle just in case theta has a full cycle of 2 pi. So we need to double that. Okay, so then theta, if I divide everything by 2, would be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so that's what we got when we solve. So then what does that mean? We're looking for the vertical tangents. So we're looking for equations let me get a different, and I want to plug these in just real quick to show you what happens here. If I plug this into my polar equation, 2 sine of, let's say the first one, pi over 4, that gives me a square root of 2. If I plug in 3 pi over 4, I get pi over 2. I'm sorry, not pi, square root of 2. Okay, and then do the same thing for the others. Now again, you have to think in polar. Because if you look at this, you might think, oh, pi over 4 and 3 pi over 4, they give me the same answer. But that's not the same point, is it? Okay, we're looking at where do these points occur. All right, so at pi over 4, that's a radius of square root of 2. But at 3 pi over 4, that's a different point of square root of 2. Now at 5 pi over 4, that's across from, this is across from pi over 4, and this is negative. So these are actually the same point. Remember how we talked about using different radius to represent the same point? And then these are also the same point. Okay, so you really have to think about that. So in this case, all we really need are this and this. Okay, we don't need the 5 pi over 4 and 7 pi over 4. But we did it anyway because we didn't know what the graph looked like. So we know that we're going to have vertical tangents at the point, so our radius is root 2 and pi over 4, and root 2 and 3 pi over 4. Okay, so that's our vertical tangents. Let's go back and do our horizontal tangents. All right, so we have y equals 2 sine squared of theta. So again, I don't want to have that squared in there when I solve. Or no, I got to do the derivative. That's what I got to do. My bad. So that would be 4 sine of theta times cosine of theta. Again, if you bring down the power, the 2, and then do the chain rule, that's what you'll get. What I don't want is I don't want the sine and cosine when I'm trying to solve. So again, this part, keep in mind that 2 sine theta cosine theta is our double angle. All right, so I'm still going to have a 2. I'm going to split up the 4 and do a 2 and a 2. Okay, so this part is your double angle, but I still have that little 2 left over. So this is 2 sine of 2 theta. All right, now I'm going to solve and set it equal to 0. All right, so 2 theta is going to be 0 to pi. And then so theta is going to be 0 and pi over 2. Okay, again, I didn't go as far because I knew that the cycle was shorter. So notice, first of all, that these points, what I get for theta here and what I get for theta here are different. That's what we want, right? Because we don't want dx d theta and dy d theta to equal 0 at the same time simultaneously. So that means at the same point. All right, so we're good there. We don't have to worry about any no conclusions or anything like that. We still have to figure out, okay, let's make sure these are different points. So we'll plug them in. So 2 sine of 0, that gives me 0. And then 2 sine of pi over 2, that gives me 2. So our horizontal tangents occur at the point radius is 0 and the theta is 0, and at radius 2, theta is pi over 2. Okay, so now I want you to look on page 735, just so you can familiarize yourself with all the different types of polar graphs. Look at the limacon, the cardioid, the rose curve, the lemniscate, and the circle. So sometimes it just gets helpful the more you work with these equations to know what to expect when you graph it. Otherwise, you can just, plug in some points and see how it graphs out. You can also graph this out on your graphing calculators. So if you wanted to grab those, it's just when you put in your function, you just have to change the type. So remember how I showed you how to change the type to a differential equation? It's under the same menu. Okay, so I just want you to be able to feel comfortable knowing what these graphs look like. Okay, so now that we've talked about horizontal and vertical tangents, we need to talk about tangent lines that occur at the pole. All right, so these are kind of important. Let's look at page 734 real quick. So pause if you need to get your books back out. Okay, so on the right, 735 are all the different kinds of polar graphs. On the left, I want you to look at that bottom graph, and you can see how we have a rose curve there. And the tangents at the pole occur in different spots because the graph reaches the pole several times throughout its cycle. All right, so that's what we're going to be wanting to find. Okay, so we're not just, notice that those are not horizontal and vertical tangents, so we want to be able to find those special tangents as well. All right, in your notes it says this happens if f of alpha, so alpha is just when, notice here, alpha is just the thetas where our f of alpha equals 0. So if we have f of alpha equal to 0, so again, I have my radius is 0, so we're at the pole. I'm going to have a tangent as long as f of alpha equals 0 and f prime of alpha does not equal 0. That really comes from the idea of our dy dx. So think back to our dy dx. I'm going to use this space down here and I will erase it. So if you need to pause it to write things down, then please do so. So remember our dy dx was the, I'm gonna write it in a different order. I'm gonna put the f primes first. So f prime of theta, but this time I'm gonna replace it with alpha because we're talking specifically about these angles where we're at the pole. Okay, so the numerator would be f prime alpha sine alpha plus f alpha cosine of alpha. So all we're doing is looking at that derivative with alphas filled in. All right. So if we have f of alpha is equal to 0, then these pieces right here become 0, right? So that's just going to be 0 times cosine, 0 times sine. So when that happens, we have f prime of alpha sine of alpha over f prime of alpha cosine of alpha. All right, so as long as they're saying, as long as f prime of alpha is not equal to 0, because we don't want zeros here. If we did, then we would have some indeterminate thing going on there. All right, so keep in mind, these are occurring at the poles. So I would have the f primes would cancel, and I would just have sine of alpha over cosine of alpha. All right, well, what's sine over cosine? That's just tangent. And tangent of alpha gives us, remember how we said that was the way to convert from your rectangular to polar. It gives us those those lines, right? We did one like that earlier. So that gives us those tangent lines that occur at the poles. So that's kind of the why behind why when we look for tangents at the poles, we want the f of alpha to equal 0 and the f prime of alpha to not equal 0. So I'm going to erase this. So let's do that. Let's do an example. So we're going to graph this polar equation and then find the tangents at the pole. So if you look at this, we should recognize this is a rose curve. And since n equals 2, so that should be, that's even, so that means we should have 2n petals. So that would mean that I have 4 petals. Okay, and a equals 1. So then that radius should be 1. So we should expect it to look something like this. Oh, nope. Did that wrong. Back up. Now again, if you don't know how that looks, that's okay. Plug in some points, right? You can always do that. Or look at your calculator. Keep in mind though, on AP, they might have you do some of these simple ones without a calculator. So it's important to know how to graph this without a calculator. It's important to know both, right? Because if you have a graphing calculator, then that'll save you some time, because this is a little time consuming. All right, so I'm going all the way to 2 pi, and I can kind of anticipate that if I know it's a 4 petal, because I have to go through all the petals. All right, so at 0 it's 1, pi over 4 it's 0, negative 1, 0, 1, 0, negative 1, 0. All right, so then you could say, okay, at 0 it's 1, pi over 4 is 0, then pi over 2 I'm at negative 1, so that's here, so it's tracing it like this. Okay, and then pi over, or yeah, we just did that. 3 pi over 2 is 0, so then I come back to 0 again, and then at pi I'm at 1. Okay, 5 pi over 4 I'm back at 0, and then 3 pi over 2 I'm at negative 1, so 3 pi over 2 is down here, go to negative 1. And then that's how it's traced out. Okay, so we know what it looks like. That's our graph. Now we want to find the tangents at the pole. So we want our f of alpha to equal 0. Remember, f of alpha is the same thing as r. r is equal to cosine of 2 theta. So we want to set that equal to 0. Our radius is equal to 0. All right, so again, we've already discussed this. Why we need to extend that out, because alpha needs to be a full cycle of 2 pi. So we're talking about pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So, and we could actually see that if we charted it out. Those are the values where we're getting a radius of 0, right? So that's when that graph occurs at the pole. All right, so then we have to do f prime of alpha. So this is r prime. All right, so if we do r prime, that's negative 2 sine of theta. We're going to set that equal to 0, because remember we don't want it to equal 0. So in order to find that, we need to figure out, well, when does it equal 0? Forgot about that. Sorry. So we're just solving for a 2 theta. Remember to go further. All right. So then if we divide by 2, we're getting this. Okay. So we want to make sure that theta is not equal to these. So remember, we don't want these. All right, so if we look at our thetas from when we solved the original for equal to 0, none of those are occurring down here. So there's nothing in common. Okay, so that just means we're going to have tangents at all of those different thetas. So the tangents at the pole are, and remember the actual lines, those straight lines, the tangents are the theta. That's the whole equation. So these aren't points, right? These are actual equations of the lines. Versus before, we just said, where do the horizontal and vertical tangents occur? Okay, so there you go. There's polar and derivatives. And now you can work on your homework.